The Sun is the star at the center of our solar system, but it is just one of billions of stars in the Milky Way galaxy, which is one of billions of galaxies in the universe. The universe has no center, and every star and planet is at the center of its own local system, due to the expanding nature of space itself. The Sun is crucial for life on Earth, but it is an ordinary star, not the sun of the universe. The Sun is an average star that serves as the center of our solar system, while the universe is the entirety of all known and unknown matter, energy, space, and time. The Sun is a yellow dwarf star, a massive ball of hydrogen and helium gas that formed about 4.6 billion years ago. When considering other stars in the universe, it is an average-sized star, while the largest known star is UY Scuti, a red hypergiant that is over 1,700 times larger than the Sun. The Sun appears large and bright to us only because it is the closest star to Earth and located just 8.2 light-minutes away. The next closest star is Proxima Centauri, a red dwarf with 2 confirmed planets, about 4.24 light-years away from our solar system, and it is a red dwarf star, a part of the Alpha Centauri star system, and is visible from the southern hemisphere. Our solar system consists of the Sun, a G-type main sequence star, and all the celestial objects bound to it by gravity, including 8 planets, dwarf planets, moons, asteroids, and comets. The Sun accounts for over 99.8% of the system's total mass. The Sun is a massive ball of hot plasma, primarily hydrogen and helium. The solar system formed from a nebula that collapsed under its own gravity, with the Sun forming at the center, and the rest of the material accreting into the planets around it. The Sun's immense gravitational pull keeps everything in the solar system, from the largest planets to the smallest asteroids and comets, from flying off into space. Planets, dwarf planets, asteroids, and comets all follow a path that revolves around the Sun. Moons orbit planets, but the planets themselves are still orbiting the Sun. The Sun emits charged particles in what is known as the solar wind. This creates a heliosphere that surrounds the solar system and can cause phenomena like the auroras on Earth. It is the primary source of light and heat, and its energy is essential for life on Earth. The Sun's energy also influences Earth's weather, seasons, and climate. The Sun formed approximately 4.6 billion years ago from a collapsing cloud of gas and dust called a solar nebula, possibly triggered by a nearby supernova shockwave. As the nebula collapsed, it spun faster and flattened into a disk, with the majority of the material clumping at the center to form a hot, dense protostar. When the pressure and temperature in the core became immense, nuclear fusion of hydrogen into helium began, and the Sun was born, with the remaining material in the disk forming the planets and other bodies in the solar system. We can summarize the steps in the formation of the solar system according to the nebular theory as: first, formation of a nebula, then nebula collapse, then formation of a protostar, then formation of a protoplanetary disk, then formation of planetesimals, then formation of planets and other celestial bodies. At last, ignition of the Sun. The Sun produces energy through nuclear fusion in its core, a process where its immense gravity compresses hydrogen atoms into helium. The main fusion process in our Sun is called proton-proton chain, which converts matter into energy every second. The Sun is composed primarily of hydrogen and helium, with hydrogen making up about 73% of its mass, and helium about 25%. The remaining 2% consists of trace amounts of heavier elements, such as oxygen, carbon, neon, nitrogen, magnesium, iron, and silicon. The Sun exists as a massive ball of hot plasma, not a solid object, and its composition is measured by mass in its visible outer layer, the photosphere. The overall composition of Sun is considered typical for stars in general. The composition of the Sun's core has changed over its lifetime, with the proportion of helium increasing, as hydrogen is continuously fused into helium. Interior of the Sun is structured in 3 layers: the core, radiative zone, and convective zone. Core is the Sun's center, where temperatures and pressures are so high that nuclear fusion occurs, converting hydrogen into helium and releasing immense energy. Radiative zone is surrounding the core. Energy from the core is transported outward by photons that are absorbed and re-emitted by plasma particles. Convective zone is the outermost layer of the solar interior, where energy is transported by the movement of plasma, as hot plasma rises and sinks back down as it cools at the surface. The Sun's atmosphere consists of 3 main layers: the photosphere, visible surface; the chromosphere, a layer above it; and the corona, the outermost layer. Photosphere is the visible surface of the Sun, from which the light we see is radiated. It is covered in granules, which are boiling cells of plasma. Chromosphere is the layer above the photosphere, where the temperature rises significantly. It can be seen as a faint pinkish ring during a total solar eclipse. Corona is the outermost layer, which is a vast and extremely hot halo of plasma that extends millions of kilometers into space. This is the layer that is visible during a total solar eclipse as a faint, pearly halo. The temperature increases dramatically from the photosphere, around 6,000 degrees Celsius, to the corona, millions of degrees. The atmosphere is composed mainly of hydrogen and helium in a plasma state. The solar wind is a phenomena, originates from the corona, where charged particles like protons and electrons are heated to such high temperatures that they escape the Sun's gravity. When directed toward Earth, it can cause minor disturbances in Earth's magnetosphere, but our planet's magnetic field usually protects us from its effects. The surface of the Sun, called the photosphere, is the visible layer of hot plasma that we see, and this layer is about 400 to 500 kilometers or 250 to 300 miles thick. It is not solid but a bubbling, granular layer that is about 5,500 degrees Celsius or 10,000 degrees Fahrenheit, which is hot enough to melt any solid material, but it gets even hotter in the layers above, such as the corona. Features like sunspots and solar flares are visible on the photosphere and are caused by the Sun's magnetic activity. The Sun is a giant sphere of plasma, which is a superheated state of gas and lacks a solid surface, like Earth's. Photosphere is the Sun's visible surface, which literally means sphere of light. The photosphere has a grainy, bubbling texture, caused by convection cells beneath it, similar to boiling water. Sunspots are large, dark, and cooler areas on the photosphere that are caused by intense magnetic activity. Solar flares are sudden and powerful bursts of energy that originate from the sunspots and are ejected into space. Above photosphere, there is chromosphere, which is visible as a red ring during a solar eclipse, and then the corona, the outermost layer that extends millions of kilometers into the space. Sunspots are temporary, darker, cooler areas on the sun's surface caused by intense magnetic activity. These planet-sized regions are cooler than the surrounding photosphere, which makes them appear dark and are often associated with solar flares and coronal mass ejections. They appear in pairs with opposite magnetic polarity, and their number varies over an approximately 11-year cycle. Sunspots are cooler than the rest of the sun's surface around 4,200 degrees Celsius, compared to the usual 6,000 degrees Celsius in the photosphere. They appear dark only in comparison to the much brighter surrounding areas. They are caused by powerful magnetic fields that burst through the sun's surface, inhibiting the flow of heat from the sun's interior. A sunspot has a darker central area called the umbra, surrounded by a lighter outer region called the penumbra. The magnetic fields emerge from the sun's interior, and the regions where they break through the surface create the sunspots. The strong magnetic fields prevent convection, which is the process that transports heat to the surface, resulting in a cooler, darker spot. Sunspots are indicators of the sun's activity, and a high number of sunspots, known as the solar maximum, correlates with more frequent solar flares and coronal mass ejections. A solar prominence is a large, bright feature of plasma that extends from the sun's surface, appearing as a loop or arc in the corona. When viewed against the bright solar disk, the same feature appears dark and is called a filament. These features are anchored to the sun's surface by magnetic fields, can last for months, and sometimes erupt violently, and potentially causing solar flares or coronal mass ejections. Prominences are made of superheated, electrically charged gas called plasma, primarily hydrogen and helium, that is guided by the sun's magnetic field. From the side, the limb, prominences appear as bright, often looped structures. Against the solar disk, they appear as dark lines, called filaments, because the cooler plasma absorbs the light from the surface behind it. The plasma in a prominence flows along tangled magnetic field lines generated by the sun's internal dynamo. Prominences are anchored in the sun's lower atmosphere, photosphere and chromosphere, and extend out into the corona. Solar prominences are difficult to see because they are outshone by the sun's brightness. The best time to view them is during a total solar eclipse, when the moon blocks the sun's glare, making the prominences visible as a reddish glow around the lunar limb. Solar granules are small, bright, cellular features that cover the sun's visible surface, the photosphere, and are the visible evidence of convection currents within the solar interior. They give the sun a mottled or boiling appearance. Hot plasma rises from the sun's interior in the center of the granule. This material then spreads across the surface, cools, and sinks back inward along the darker edges, known as intergranular lanes. The center of a granule appears brighter because the rising plasma is hotter, around 6,600 Kelvin. The cooler, sinking plasma at the edges appears darker by comparison. A typical granule is enormous, with a diameter of around 1,000 to 1,500 kilometers, about the size of a large country or the state of Texas, which is still a very small part of the sun's total surface. Individual granules are short-lived, typically lasting only 8 to 20 minutes before dissipating and being replaced by new ones. The plasma flow within granules can reach supersonic speeds of over 7 kilometers per second, generating acoustic waves, sonic booms, on the solar surface. Solar granules cover the entire photospheric surface, except where there are sunspots. A solar flare is a sudden, intense brightening on the sun's surface, specifically its atmosphere, resulting from the explosive release of magnetic energy that has built up near sunspots. They are the most powerful explosions in the solar system, emitting massive bursts of electromagnetic radiation from radio waves to X-rays and gamma rays, which travel at the speed of light. Solar flares occur in active regions, typically around sunspot groups, where intense, twisted magnetic fields penetrate the sun's surface. When these fields become too tangled and unstable, they snap and reconnect in a process called magnetic reconnection, releasing immense amounts of energy that heat plasma to millions of degrees and accelerate charged particles to near the speed of light. The frequency of solar flares follows the sun's approximately 11-year solar cycle, occurring multiple times a day during solar maximum and less than once a week during solar minimum. While Earth's atmosphere and magnetic field shield humans on the surface from the direct, harmful radiation of solar flares, they can still have significant impacts on technology and infrastructure like radio blackouts, satellite interference, auroras or northern lights, and affecting power grids or navigation systems, or even aviation. The sun has a large, complex and dynamic magnetic field that is generated by the movement of its electrically charged plasma, which acts like a massive dynamo. This magnetic field is the primary driver of virtually all solar activity, including sunspots, solar flares, and coronal mass ejections. The magnetic field is created within the sun's convection zone, where hot, charged plasma churns and rotates at different speeds, at different latitudes, a process called differential rotation. This motion twists and stretches the magnetic field lines. Unlike Earth's relatively simple, stable, bar magnet-like magnetic field, the sun's magnetic field is much messier and more disorganized, especially in active regions. It has both large-scale components, which approximate a dipole field with north and south poles, and small, intense, localized loops. While the sun's global magnetic field is weak, only a few Gauss, active regions like sunspots can have field strengths thousands of times stronger, reaching several thousand Gauss. The magnetic field extends far into space, carried by the solar wind, creating a vast magnetic bubble around the solar system called the heliosphere. This interplanetary magnetic field interacts with the magnetospheres of planets, which can lead to space weather events. Solar radiation is the electromagnetic energy emitted by the sun, which travels through space, and is the primary energy source for life and climate processes on Earth. It spans a wide spectrum of wavelengths, from gamma rays to radio waves. The radiation from the sun can be divided into three main regions, based on wavelength, and the Earth's atmosphere filters these differently: ultraviolet or UV radiation, visible light, and infrared radiation. Of the total solar radiation that reaches the top of the atmosphere, approximately 56% makes it to the Earth's surface. Of that portion, about 49% is infrared, 42% is visible light, and 8% is ultraviolet radiation. Solar radiation is vital for life, enabling photosynthesis and helping human bodies produce vitamin D. However, excessive exposure to UV radiation can be harmful, increasing the risk of skin damage, cancer risk, premature aging, immune system suppression, and eye damage. Solar activity such as solar flares and coronal mass ejections can emit bursts of high-energy radiation, including X-rays and gamma rays, that pose a risk to astronauts and satellite equipment in space and can interfere with communication systems on Earth. Earth is dependent on the sun for life, as the sun provides essential heat and light that regulate our planet's temperature, drive weather patterns, and enable photosynthesis for plants and the entire food chain. The sun's energy is fundamental for maintaining liquid water, providing oxygen through photosynthesis, and powering Earth's climate systems, like ocean currents and the hydrological cycle. The sun's energy keeps Earth warm enough to support life. Without it, temperatures would drop to around -270 degrees Celsius. The sun's radiation drives atmospheric circulation, ocean currents, and the water cycle, creating weather patterns and transporting water across the globe. Plants use sunlight to convert carbon dioxide and water into food and oxygen through photosynthesis, forming the base of nearly every food chain on Earth. All life on Earth depends on the sun's energy, either directly through photosynthesis or indirectly by consuming organisms that do. The sun is not constant and goes through cycles of activity where it brightens and dims slightly over about 11 years. These changes can affect Earth's atmosphere and surface. While solar activity has a minor influence, the rapid warming in recent decades is not linked to changes in Earth's orbit or solar cycles. Thank you so much for watching this video. I hope everyone enjoyed and learned a lot about our sun in the solar system and how important it is in sustaining our life. Please make sure to subscribe my channel.